Hello friends, so today we are going to do the questions from the year 2023, and this is the part 1 from the year 2023, and here we are going to solve 10 questions, and all these 10 questions are from the mains. First question, it states that in the given figure, the total charge stored in the combination of the capacitors is 100 microcoulomb. Okay, the value of X is. So we are given a figure in which we have 3 capacitors, and all these 3 capacitors are connected in parallel, C1, C2 and C3, and we are required to find out the value of our C2, whose value is given as X. So let us assume that the charge on C1 is our Q1, charge on C2 is our Q2, charge on C3 is our Q3, and all these 3 are connected in parallel. So each capacitor is going to have same voltage, that is our V, which is our supplied voltage, 10 volt. Therefore, we can find out charge on each capacitor. Charge on, let us start with C1. Let us suppose that is given Q1 will be equal to our C1 multiplied by V, which is 2 into 10, giving us 20 microcoulomb. Similarly, we can write our C2. Let us suppose the charge is given as Q2 will be equal to C2 multiplied by V, and C2 is given as X, so this comes as X multiplied by 10 microcoulomb. And finally we come to our C3. So C3 is our Q3, which will be equal to C3 multiplied by V, and it will be coming as 3 into 10, which will be 30 microcoulomb. We are given total charge is 100 microcoulomb. So in this case, the total charge will be equal to Q1 plus Q2 plus Q3. So you can write total charge will be equal to Q1 plus Q2 plus Q3. We substitute the respective values. Q1 was our 20 plus Q2 was our 10x, and Q3 was our 30 microcoulomb, and we are given that this total charge is our 100 microcoulomb. So this micro and micro cancels out, so we get this as 50 and then comes 100. So X will be equal to our 50 divided by 10, which gives us the value of X is our 5. So value of X is our 5. Next question. It states that 2 charges each of magnitude 0.01 coulomb separated by a distance of 0.4 millimeter constitute a electric dipole. If the dipole is placed in a uniform electric field E of 10 dyne per coulomb, making 30-degree angle with E, the magnitude of the torque acting on the dipole. So we have to find out the torque on the dipole, and this is directly based on the formula. We can say torque on the dipole, torque acting on dipole, that is our tau, will be equal to dipole moment, electric field, and sine of theta, that is theta is the angle between them. Okay. And here our P is our dipole moment, which will be equal to our Q times D. Q is the charge and D is the distance between them. Okay. And charge is given to us as 0.01, so you can write this as 0.01. Distance between them is 0.4 millimeter, which can be written as 0.4 into 10 to the power minus 3. 0.4 into 10 to the power minus 3. So we get this dipole moment will be equal to 4 into 10 to the power minus 6 meters, coulomb per meter. Okay. Or coulometer, I think. Coulometer. We substitute the value. We get our torque will be equal to 4 into 10 to the power minus 6. Electric field is given to us as 10 dyne per coulomb. So we can just convert into Newton and divide it by 10 to the power 5. So this comes as 10 upon 10 to the power 5 and sine of 30. So this comes as 5, this will be sine 30, okay. So we get our tau is equal to, we get this as 4 into 10 to the minus 6 into 10 to the power minus 4, and we have here sine of 30, which is 1 by 8, 1 by 2. So therefore we get tau will be equal to 2 into 10 to the power minus 10 Newton. So tau is equal to 2 into 10 to the power minus 10 Newton meter. So option number 2 is the correct one. Option 2 is correct. Next question. In this question it states that a thin infinite sheet charge and infinite line charge of respective charge density plus sigma and plus lambda are placed parallel at 5 meter distance from each other. Points P and Q are 3 by pi meter and 4 by pi meter perpendicular distance from the line charge toward the sheet charge respectively. EP and EQ are the magnitude of resultant electric field intensities at point P and Q respectively. If EP by EQ is 4 by A for twice sigma is equal to lambda magnitude wise, then the value of A is. So here we are given a sheet, infinite sheet charge. So let us draw a sheet charge. So sheet charge, let us suppose it is something like this, and charge density is given to as positive to us, and we have a line charge. Let us suppose this is somewhere here, and here also it's given as positive. Here it is a sigma and here is given as lambda. And with respect to this line, we are having 2 points P and Q. Okay, so let us draw a line toward the sheet, and we are having 2 points. One point is P and other point is our Q. Distance of Q is given as 4 by pi and distance of P is given as 3 by pi. And the distance between the sheet and the line charge is given as 5 meters. We have to find out, or rather we can say we are given that the resultant electric field intensity at point P and its ratio with Q is given as 4 by A. And we are given another relationship that the magnitude of our sheet density, charge density is equal to magnitude of our line density, line charge density. Okay. And we are going to find out the net electric field EP at EQ. Okay. So we know the basic formula, and for our infinite sheet, so we can say electric field due to infinite sheet, and let us suppose we write that as E sheet, which will be equal to charge density divided by 2 epsilon naught. In case of sheet, we have to keep in mind that the electric field is independent of the distance. It means how much distance this P and Q are from our sheet, it doesn't matter. Okay. And next is our with respect to line charge. So we can say our electric field due to infinite line. Infinite line. Let us call this as E line, and E line will be equal to our charge density divided by 2 pi epsilon naught and R. R is the distance of the point. Here point will be our P, and the second case it will be our Q. And if you direction wise, so this sheet is going to have a direction away from the sheet, or we can say towards the line. So we can say its direction will be toward line, or we can say toward right side. And the direction of the electric field due to line, this will be towards the sheet. Toward the sheet, or we can say toward left. Let's find out the, can say, okay, the line we can just update the equation using the relationship that lambda is equal to twice of sigma. Okay, so therefore we can write that our electric field due to line will be equal to twice of sigma divided by 2 epsilon naught times R. Here 2 and 2 cancels out. This comes as our sigma upon pi epsilon naught multiplied by r. So therefore, the net electric field due to the line, because for sheet it will be same. So we can write for point P, we can write our electric field EP will be equal to our sigma upon pi epsilon naught, and distance is our 3 by pi, minus because of the sheet, and that will be same independent of this. So this comes as sigma upon 2 epsilon naught. Here pi and pi cancels out, so this comes as 3 epsilon naught. 3 epsilon naught minus 2 epsilon naught. So it will be our LCM will be our 6. So this comes as our let me epsilon naught, and this comes 1 by 3 minus 1 by 2, 1 by 3 minus 1 by 2. Okay, so LCM will give us 6. So we can say our EP magnitude wise will be equal to 1 by 6. So this comes as 6 sigma upon 6 epsilon naught. Similarly, we find out for point Q. For point Q, our EQ will be equal to, because of the line, so we get sigma upon pi epsilon naught, and distance is given as 4 upon pi minus 4 upon pi minus, for the sheet it will be same, 2 epsilon naught. Pi cancel with pi, this comes as sigma upon 4 epsilon naught, we can take as common, sigma upon epsilon naught, in it comes as 1 by 4 minus 1 by 2, and 4 will be LCM, so this comes as 2, and it will be our, so we can write our E of Q will be equal to sigma upon epsilon naught. 4 is our LCM, and this comes as 1 minus 2, and from here we can say our E of Q magnitude wise we get this as sigma upon 4 epsilon naught. We are going to find out a ratio, so we can say our EP upon EQ will be equal to, and EP is our sigma upon 6 epsilon naught divided by sigma upon 4 epsilon naught. Here epsilon naught sigma cancels out, and this comes as our 4 by 6, which will be our 2 by 3. But we are given that this ratio is equal to 4 by A. Therefore, we need to find out value of A. So we can say that our, let me write it here, 2 by 3 is our 4 by A. So we can say our A is equal to, we get this as goes by 2, and which gives us A will be equal to 2 into 3, that is 6. So the value of A is 6. Next question. It states that in the network shown below, the charge accumulated in the capacitor in steady state will be. Basic figure is given to us. We have supply voltage V in series with a 4 ohm resistance. Let us call this resistance R1. We have capacitor. Let us call this as C, and the 6 ohm, let us call this as R2, and we have another 6 ohm, that is called this as R3. So in the steady state, this capacitor is going to behave as an open circuit. Okay, so no current will be flowing in this particular branch in steady state. Okay. So we can say that in steady state, capacitor C acts as open circuit. Therefore, we can just modify the given figure and it can be drawn so we have our R1 and our R3, and we have a voltage source. Let us suppose we call this as V, which is our 3 volt, and the current in the circuit, let us call this as I. So this current I is only dependent upon our R1 and R3, because R2 is not in the picture. It is open circuit, no current is flowing through it. Therefore, we can say that current I will be equal to our supply voltage V and divided by our R equivalent, and R equivalent will be equal to R1 plus R2. So this will be V upon R1 plus R2. So we get our current I. V is our 3, R1 is given as 4, and R3 is given as 6. Sorry, it is R3. So this comes as 6 plus 4, which gives us that the current I will be equal to 3 by 10 amperes. And this okay, so here the capacitor is our open circuit. So let us approximately, so this is open circuit, and we have a resistance, this is our R2. So this entire circuitry, that is a capacitance and R2, is in parallel with R3. So the voltage drop across our R3 will be indirectly the voltage drop across our capacitor, or the parallel circuit of capacitor and resistance. Okay. Therefore, we can say that voltage drop across R3 will be equal to current multiplied by our R3, and we substitute the value. Current is our 3 by 10 and R3 is our 6, so this comes as 18 by 10 volts, which is 1.8 volt, and this entire will be our across the capacitor. This, or we can say thus, capacitor C will have same potential. Let us call that potential as VC. So VC will be equal to 1.8 volts. We need to find out the charge on capacitor. So we can say charge on capacitor, let us call that QC, will be equal to C multiplied by our VC, and C is given to us as a 4, and this is 1.8, and this is micro coulomb. So we get this as charge on capacitor C, capacitor is equal to 7.2 microcoulomb. So option number 1 is correct. Is correct. Next question. We are given 3-point charges Q minus Q and plus 2Q are placed on x-axis at a distance x is equal to 0, x is equal to 3r by 4 and x equal to r respectively from the origin as shown. If Q is equal to 2 into 10 to the power minus 6 coulomb and r is 2 centimeter, the magnitude of net force experienced by the charge minus 2Q is. So basic figure is given to us. We are given that the charge Q is at the origin, minus 2Q is at a distance of 3r by 4 with respect to origin, and 2Q is at a distance of r with respect to the origin. And we have to find out the magnitude of net force experienced by the minus 2Q charge. So we know that the force on, there will be two forces acting on minus 2Q. One force will be because of this Q charge and another force will be because of this plus 2Q charge. Okay. And both are, you can say, oppositely charged. So therefore there will be a Q is going to attract and minus 2Q is also going to, sorry, plus 2Q is also going to attract it. Okay. So net force will be our subtraction of both. So let us call this as force as F1 and we call this as force as F2. Capital R is given to us 2 centimeter. So we can, let us suppose this distance is our, we need to find out this distance. So this comes as 3r minus 3r by 4. Yes, so we can say this will be over r minus 3 by 4 times r, which will be coming to us as r by 4. Okay. And we are given that r is 2 centimeter. Okay, so we can just, so r is about 2 centimeter, so this comes as 2 by 4 is equal to 1 by 2 centimeters. And in terms of meter, we can write this as our 0.005 meters. Let us call this as our R2. Similarly, we can find out this portion, that is our R1. Let us call this as R1. R1 will be equal to our 3 by 4 times R, that is 2 centimeter, and also it will be coming as 3 by 2. So we can say our R1 will be equal to 0.015 meters. So we found out our R1 and R2. Now we can just use the force formula, Coulomb's law basically. So we can say force between 2-point charges, force between 2-point charges. The general formula is our F is equal to KQ Q1, Q2 and R square, where K is the constant value is 9 into 10 to the power 9. So we can divide this formula according to the forces. So we can say between plus Q and between plus 2Q and minus 2Q, and we call that force as our F1. We call that as F2. Okay, let us do F2 first. So that F2 will be equal to our K times minus 2Q multiplied by plus 2Q divided by R1 square, and F2 we can write this will be coming as 4 times K Q square upon R1 square. So we just substitute the values, 4 into 9 into 10 to the power 9, and charge is 2 into 10 to the power minus 6, and R1 we found out is our 0.015 whole square. So this force we are going to get, this will be about 5760 Newton. Now we find out between our minus 2Q and plus Q. So we get this as our F1 will be equal to, this comes as our K minus 2Q multiplied by plus Q and divided by our R2 square, and this comes as our 2K. So we can write this as 2 into 9 into 10 to the power 9 multiplied by Q square. Here it is square 2 into 10 to the power minus 6 whole square, and our R2 is 0.005, and this is whole square, which gives us 320 Newton. That force is the difference between the two. So net force, let us call that as F, will be equal to our F2 minus F1. F2 is our 5760 minus 320, and this comes as 5440. F2 is greater than F1, so net force will be towards right. So magnitude of force experienced by this is our 5440 Newton. Next question. We are given, in the circuit shown, the energy stored in the capacitor is n microjoule. The value of n is. So obviously it is talking about the steady state condition. So the capacitor will be our open circuit. So we can just redraw the circuit, and we have here 12 volt, and this is our voltage source of, resistance of 3 ohm, and this is our resistance of 9 ohm, and here we have a resistance of 4 ohm, and this is a resistance of our 2 ohm, and the capacitor is our open circuit, which should be something here. So we have this 12 volt supply is given to us. Let us suppose the current flowing through here is our I1 and here is through I2. Now the voltage source is in parallel with our both 3 plus 9 and here it is parallel with 4 plus 2. So therefore, first of all let me write that at steady state capacitor, let us call this as our R1, R2, R3, R4 and capacitor is C. Capacitor C acts as open circuit, and so this was our C, so we can say, and we have this as our R1, R2, R3 and R4. Therefore our I1 will be equal to supply voltage, let us put that is V divided by R1 plus R2. V is our 12 and this comes as 3 plus 9 giving us 1 ampere. Similarly, we can write that our I2 will be equal to our V divided by our R3 plus R4, and V is our 12, 4 plus 3 is 4, plus 2 will be our 6, so this comes as 2 ampere. We need to find out the energy stored, and energy stored is our half CV square. Capacitor we know, we need to find out what will be the voltage. We call this as, this point is our A and this is our B, C and D. Okay, so this common point will be our A and this will be C, D and this common point will be our B. So we need to find out the potential between C and D. Okay, potential difference between C and D, which will be giving us a voltage drop across the capacitor. Let us suppose that is VC. So we are going to find out VC minus VD, and in order to find out VC minus VD, we are going to use the basic, we can say, voltage divider we can use, and with respect to current we are given, so we can say that our VA minus VC. Okay, so let me draw it here. So this point is our A and this point is our C, and the current flowing through this is our I1, which is our 1 ampere. Here I am drawn only the partial circuit, so circuit is complete, so obviously the current will be flowing, and current is going to flow because of the potential difference. So let us suppose the potential difference here is our VA and here it is our C. Therefore for this we can write that our VA minus VC and this resistance we have called as R1 will be equal to R1 multiplied by I1, which is equal to R1 is given to us as 3 multiplied by 1, this gives us 3. So we get our VA minus VC is equal to 3. Let us call the equation number 1. Similarly, we can draw for our CD. So this point is our C, this point is D, and here also current flowing is our, sorry, one second, D, not CD. We get this as, this point is A. Current flowing here is I2, which we know is our 2 ampere, and the resistance is our R3. Let us suppose we already know the voltage at VA is VA, and for D we call this as VD. So we can write VA minus VD will be equal to I2, and we have this as our R3. I2 is our 2 and our R3 is given to us as 4. So this comes as 8. Therefore, we can write our VA minus VD is equal to 8. Let us call this equation number 2. So if we subtract equation 1 and 2, we can easily get VC minus VD. So we can say subtracting subtracting 1 and 2. So VA cancels out and we get this as our VC minus VD will be equal to 8 minus 3, that will be giving us 5. So the potential decoder of the capacitor, that is VC, is equal to over 5 volts. Now we can just find out the energy. Energy stored in the capacitor. Energy stored in the capacitor. Stored in capacitor C, which is, let us suppose here U, it will be equal to half CV square. And we get U is equal to half C is given to us as 6, and for voltage we found out as 5 whole square. So this comes as 75 microjoules, and it is given to us as N microjoules. N microjoules. Therefore, the value of N will be equal to 75. Next question. It states that 64 identical drops, each charged up to a potential of 10 millivolt, are combined to form a bigger drop. The potential of the bigger drop will be dash millivolt. So we have 64 identical drops. So it means if this is drop 1 and we multiply it by 60, we are going to get a bigger drop. And let us suppose this small drop is having a radius of small r, and this bigger drop is having a radius of capital R. And here the volume will be of the 64 entire volume will be equal to, or I can write 64 into volume of single drop will be equal to volume of bigger drop. Okay. So this is volume of small drop will equal to volume of big drop. And in terms of the charge, if this small drop is having a charge of Q and capital drop is having a charge of capital Q, therefore we can write that our 64 multiplied by charge on small drop, which is our Q, is equal to charge on big drop. Charge on big drop, which is our capital Q. Therefore, from here we can write capital Q is equal to 64 times small q. And with respect to this volume, we can write this as 64 multiplied by 4 by 3 pi r cube will be equal to 4 by 3 pi capital R cube. And here 4 by 3 pi cancels out. So this gives us a relationship between the small drop and capital drop, radius of small and capital, which gives us that a capital drop radius capital R is equal to 4 times small r. And we have to find out the potential of the bigger drop. So we can just use the formula. You can say potential of big drop, let us suppose that is given as V, is equal to K, which is constant Q charge on big drop multiplied by this R. And we already know relationship between capital and small, so substitute K, we have a 64 small q divided by 4 divided by multiplied by small r. And we are going to just substitute the values. We are going to get this as this comes as 16. Value of K is our 9 into 10 to the power 9, and Q is given to us, potential is given to us, values are not given. So let me write it. So potential on big drop is our capital V, and this comes as our 16 multiplied by Q, KQ upon R, and this particular is with respect to potential on the smaller drop, which is given to us as 10 millivolt. So we can say this gives us V is equal to 16 multiplied by 10 and millivolt, which is 160 millivolt, and we get this as 160 because the millivolt is already written, unit is already present. So this comes as 160. And we have to remember this is potential of the small drop. Potential of small drop. Next question. We are given a parallel plate capacitor of capacitance 2 farad is charged to a potential of V. Energy stored in the capacitor is even. The capacitor is now connected to another uncharged identical capacitor in parallel combination. The energy stored in the combination is E2. The ratio of E2 by E1 is. So initially we are having capacitor. Okay. So we have given two capacitors. So let us say this is our capacitor C1 and this is our another capacitor which is, let us suppose, our C2, and C1 is given to us as 2 farad and C2 is also identical, so this will be also our 2 farad. It is charged to a potential of V, so we can say our V1 is equal to V and initially, and initially that is uncharged. Okay, so we can say initially V2 is equal to 0. So obviously, so this is our entire initial condition. Initial condition. So under initial condition, total energy will be only the energy that is associated with our C1, because C2 there is no charge stored on it, or there is no voltage source, voltage on the capacitor. Therefore we can write that initial energy stored, initial energy stored. Let us call this as ui. So ui will be only dependent upon C1. So we can say this as our half C1 V1 square. We substitute the value, we get our ui will be equal to half C1 is given to us as 2 and potential is given to us as V. So this is V square. 2 and 2 cancels out. So we get our initial energy is equal to our V square. Now the capacitors are connected in parallel combination. So you can say C1 and C2 are now connected in parallel. C1 and C2 are connected in parallel. Therefore, we can find out their equivalent capacitance, which will be equal to C1 plus C2, giving us, because they are same, so 2 plus 2 will be our 4 farad. And initially we can also find out the charge, and similarly the charge will be only because of C1. So we can write that initial charge let us suppose we call this as Q1, and Q1 will be equal to C1 multiplied by V1. So we get here Q1 is equal to 2 times V. So this is our initial charge, total initial charge, because here Q2, if present, that will be equal to 0. So as they are connected, there is no external voltage source, therefore the charge on the combination is going to remain same because of the charge conservation. So we can say that equivalent capacitance and total charge let us call the Q equivalent will be equal to our initial charge, that is our Q1, which is our 2 times V. Now both are connected in parallel and the potential will be same on both. Okay, let us suppose we call this as V prime. So we can say that new potential we can just draw approximately. So this is our C1 and this is our C2. Both are connected parallel with each other and the voltage will be obviously same. So here we have V prime and here also have a V prime. And the total charge on this is our 2V. C equivalent we just found out. Okay. So new potential, that's a V prime, will be equal to our Q equivalent divided by C equivalent, which gives us 2V divided by 4, comes as V by 2. So we have a new potential across both the capacitors will be our V by 2. Now we can just find out the new energy. New energy, which is given as our E2, will be equal to our half C, and this comes as C equivalent and V prime square. So this comes half C equivalent is 4, V prime square comes as V square by 4, and this will be equal to our V square by 2, because this 4 and 4 goes away, and we have given the ratio of E2 by E1. Okay, so E1 was, one second, so this was our E1, sorry. So E1 was our V square and E2 is our V square by 2. Therefore, we can say ratio E2 by E1, we get this as V square by 2 divided by V square is equal to 1 by 2, or we can say 1:2. So option 2 is correct. Option 2 is correct. Next question. We are given, as shown in the figure, a configuration of two equal point charges Q0 given as +2 microcoulomb are placed on an inclined plane. Mass of each point charge is 20 gram. Assume there is no friction between the charge and plane. For the system of 2-point charges to be in equilibrium at rest, the height h is given as x into 10⁻³ meters. The value of x is. So basic figure is given to us. We are given two charges, Q0 and Q0, both are positive. So obviously we are going to have a repulsive force between them. And Q0 is fixed at the base. Let us call this, for the sake of simplicity, as Q1, and we call this as our Q2. So Q2 is fixed at the base, only Q1 is moving. And because it is Q0 is in equilibrium, so there will be a force which will be acting in this direction up the inclined plane. That is a Coulomb force or electrostatic force. Let us call this Fe. And this is our Q1. And there will be a, okay, let me draw it here, much more easier. So this is our Q0, which is our Q1. In the downward direction, we are going to have a mg, and up the inclined plane, we are going to have a Fe. So mg we can divide into two components. So angle is, let us suppose this theta, which is our 30 degree, and this will be of mg cos of theta, and here will be mg sine of theta. As this is in equilibrium, so we can say our mg sine theta should be equal to our Fe. There will be also normal acting on it, something like this, but that is not required. Okay. And we can say for equilibrium, electrostatic force which we call as Fe will be equal to component of mg along the inclined plane. Component of mg along the inclined plane, and let us call this as Fg, which is our Fg. So we can write our Fe is equal to our Fg, and if r is the distance between the two, so this distance is of r. So we can write our Fe will be equal to K into Q1 Q2 divided by r square is equal to, and we have this as mg sine of theta. And from the figure we can clearly see that sine of theta will be equal to h upon r. So we can write it as k into, this will be q naught square upon r square is equal to our mg, and this comes as h upon r. And well, let me solve it separately. This is our sine of theta. So we can write that sine of theta is equal to over h upon r, or we can say that our theta is given to us, so we can say our r will be equal to h upon sine of 30. This gives us that r is equal to 2 times h. So we can just substitute it, and we'll be getting this as k multiplied by q naught square, and our r is 2h whole square is equal to mg multiplied by we have here 30, that is 1 by 2. So therefore we are interested in finding the h, so we can say our h will be equal to, this will be coming as 4, so we get this as k q naught square multiplied by 2 divided by 4 times mg and its square root. So this goes by 2, and we get our h is equal to k q naught square divided by 2 mg. So this is the value of height h. We are given all the respective values. Now we simply plug them. So we get h is equal to, k is our 9 into 10 to the power 9, charge is given to us as 2 into 10 to the power minus 6 whole square, and this is 2, m is our given as 20 gram, so this will be 0.02, and g is our taken 10. So this gives us our h will be equal to 0.3 meters. But the given expression for the h, let me write it, this h is 0.3 meters, but the given expression for h is our x into 10 to the power minus 3. So which gives us that value of x will be equal to 300. X is our 300. Next question. We are given that a capacitor of capacitance C is charged to a potential V. The flux of the electric field through a closed surface enclosing the positive plate of the capacitor is. So let us draw a capacitor. So this is our capacitor, and let us assume that our left plate is our positive plate and the right plate is obviously our negative plate. And if the total charge on this entire capacitor is capital Q, so left plate is going to have a plus Q charge, and and right plate is going to have as a minus Q charge. and it states that we have to find out the electric field, the flux of electric field through. Okay, so you can say that this charge Q on the capacitor, if it is having a capacitance of C and potential difference V, then we can say charge on capacitor, which is our Q, will be equal to C times V. So positive plate, that's the left one, will be holding a plus CV charge, and on the right plate it is going to have a charge of minus CV. And we are interested in the flux. So if we draw a Gaussian surface about the positive plate, so from here we can say that the flux enclosed will be equal to our charge enclosed divided by epsilon naught. A charge enclosed is our Q divided by epsilon naught, which is equal to CV divided by epsilon naught. And sign, let us put, for the sake of convenience, this will be our positive charge. I think this was the last one. Yes. So this was the part 1 from the year 2023, and in this part 1 we solved 10 questions, and all these 10 questions from the mains only. Remaining questions we are going to deal in part 2, if required part 3, and I think part 4 won't be required, but if required we can just extend it to the part 4 also. Okay, later on we are going to also cover in part 3, possibly we are also going to cover some of the advanced questions that were asked in the year 2023. So this completes the questions. Thank you.